Quantile methods, and probably I will stop more or less at the usual time before I say something that I regret at the end. So I'm just going to run through some fairly basic stuff and then talk about things that are a little more recent in dealing with endogeneity and some panel data issues with when doing quantile regression, including least absolute deviations. So let me just start with some, I guess, what I would call reminders about means and medians and quantiles. So this is often introduced in the context of a linear model with, of course, some covariates and then an error term. So I want to focus on the case where the error term here has a finite variance, so that even though the distribution could be spread out, it's not so spread out that there's an infinite variance in the error term. So if we ask a basic question, because certainly least absolute deviations is a method that has become more and more popular, at least often as a supplement to least squares, if not as the primary method of interest. It's important to understand when we should expect these to produce similar estimates and when we should fully expect them not to and not be worried about that. So, of course, least squares solves minimizing the sum of squared residuals in 2, and least absolute deviations minimizes the sum of least absolute errors in 3. So when should we expect these to provide similar estimates, which is basically just saying when are the population parameters that solve these two problems the same? Well, there are two cases that are important, and the first is when the distribution of u in this equation is symmetric conditional on x, and it might as well be symmetric about 0 then. In that case, of course, the mean and the median are the same, and so we would expect, at least under the case where there aren't, influential observations, that these will provide similar estimates. Certainly, the population values that solve these two equations in the limit are the same. So one condition is symmetry. The other case, and this, of course, allows the distribution of u to depend on x. So there could be heteroscedasticity here, right? It's just the expected value of u given x is 0, the median of u given x is 0, and so OLS and LAD have the same probability limits in that case. Now, another case is where this error term is independent of x, and we have to have some normalization. So let's just say the mean is 0. We could say the median is 0. The point wouldn't change. So if the error term is actually independent of the x's, then the OLS and LAD estimators, they both identify the slopes beta. Of course, the intercept will generally be different because if u has an asymmetric distribution, then the intercept for LAD will converge to some, alpha plus eta, and of course the OLS estimate of the intercept will converge to alpha. So the point of actually going through these two cases is that in lots of cases where one is interested in doing least absolute deviations, you suspect that neither of these assumptions is true. Independence is quite strong because at a minimum it rules out heteroscedasticity, right, in the error distribution. Symmetry is quite strong also because often one of the reasons we apply least absolute deviations is because we think the effect on the median might be different than the mean effect. And so it's not so much that when we find differences between OLS and least absolute deviations that we should conclude that, there must be an outlier problem or something. A perfectly sensible explanation is that the conditional median and the conditional mean are different, and they're different in a way that's more than just this additive constant on the end. So this is a basic point, but again, the focus often is on resiliency to outliers, and then somehow if you find a difference between these two, that means something is wrong with OLS, when in fact it just might be that they're approximating two different objects. OLS, of course, is trying to approximate the mean, and least absolute deviation is trying to approximate the median. Of course, neither of those might be linear, in which case we still don't expect them to be similar because they're approximating different things. So, of course, least absolute deviations is more resilient to outliers or changes in extreme values because, well, the median is certainly a lot less sensitive than the mean is to such changes. So that's just really, in some ways, a consequence of the object that we're trying to estimate. The median is less sensitive to changes in the tails of the distribution, and the mean, of course, can be quite sensitive. Okay, so that's just one point that certainly sometimes the language in applications seems to be that it's really just an issue of being resilient to outliers which is why people use least absolute deviations. This is also kind of, if you look at other what are called robust estimators that are intended to be insensitive to outliers, virtually all of them do rely on a symmetric distribution because they might do something like use a squared residual up to a point and then actually flatten out so that you don't give any additional weight to large residuals. Again, those are almost always derived under the assumption of a symmetric distribution, and so they're robust in the sense that they're insensitive to outlying data, but they're not what we would call a robust estimator of the mean in general because they impose symmetry, and of course, to estimate a conditional mean, we don't need a symmetric distribution. Okay, now just a couple of other things that will come up later. There are some advantages that medians have over means, and some of these carry over to quantiles as well. And then there are some advantages means have over medians. So one big advantage of the median operator is that it passes through monotonic functions. So if you start with a model like this, say, this isn't the most interesting example, but we'll come to those later on. We start with a model for log of y, linear, and assume that the median of u is 0, conditional on x. Then, of course, the median of y itself is just the exponential of the median of log y. And this is not true, of course, for the mean, where the mean does not pass through nonlinear functions. In this particular case, you can characterize the mean even though you can't necessarily find it. It's the exponential of the mean of log y in this case if u actually has a 0 conditional mean, but then there's this extra part at the end which in general would be a function of x. Okay, so this basic point was key in the early development of least absolute deviations for things like censored regression models, right? That you couldn't characterize the mean without knowing a lot more about the distribution of the unobservable, whereas the median was easily obtained because the transformations are monotonic in the underlying variable. Okay, but let's not forget about some properties that the conditional mean has that the median does not share. Two of those that turn out to be fairly useful generally are the expected value is a linear operator and the median is not. So the other useful probabilistic feature of expectations is the law of iterated expectations, and there's no law of iterated medians, which is unfortunate actually. That makes it quite a bit harder to figure out sensible ways to do things like least absolute deviations when you have panel data with unobserved heterogeneity, for example, We'll talk about that in a little bit. But just to show you an example where maybe we don't think about these issues as much as we should, if we started with a general random coefficient model, as in 6, so again, this intercept plays the role of the usual additive error, and then we have these random slope coefficients. Well, if we made the kind of typical assumption, which is that the heterogeneity is independent of everything, well, what would we need to do to consistently estimate something interesting by least squares, say? Well, if under independence, then we have this expression in 7, so that the regression of y on x, of course, identifies the average, the population averaged effects. Okay, that's very basic. And of course, this would imply some sort of heteroscedasticity in y given x, but we certainly don't need to even know what that is in order to consistently estimate alpha and beta. Okay, so if we just take the basic linear model, we add this feature, then clearly, of course, OLS is going to consistently estimate something interesting in that case. By contrast, there's really no, if we maintain independence between the heterogeneity and x, you really can't do anything with the median unless you add some more assumptions. And so in this particular case, you would say, well, if you just wanted to say the key assumption is that heterogeneity is independent of the covariates, you wouldn't be able to get very far with the median. There are, of course, assumptions that one can add to make sure that the median, that least absolute deviations does estimate something interesting. And the one issue is how one goes about defining symmetry in a multivariate context, or what kinds of assumptions are sufficient in order to be able to figure out what medians are of linear combinations. And one general definition that has come up is, I guess I cut that off on the slide, is this notion of a centrally symmetric distribution. And so suppose we have a random vector ui, and whether we condition on x's is not that important, although in this context it is relevant. The distribution is said to be centrally symmetric if the distribution of u is the same as the joint distribution of minus u, conditional on x. This has the implication that if we take, because this is conditional on x, then if we take a linear combination of these errors, which could be functions of x's, then this has a univariate distribution, which is symmetric. So in particular, then, the expected value would be symmetric about 0. So the expected value of u has to be, given x has to be 0 in this case also. So if we start with that and then rewrite the equation in this way, and we assume that the heterogeneity consisting of A and B is centrally symmetric, then this additional term does have a conditional median that's equal to 0, and then we would actually be estimating the same alpha and beta that we estimate with least squares. Now, we'll come back to this because while this example is not especially interesting, I think, it does, this notion of centrally symmetric is a pretty strong restriction, and it's hard to relax it actually and get any kind of usable results in this particular case. So methods such as quantile methods, generally least absolute deviation specifically, they don't naturally apply to cases where you suddenly take basic models with a single additive error and now replace that with models where there are heterogeneous slopes. Okay, so let's talk a little more generally about quantile estimation. Remember, generally this is the definition of a quantile. If we focus on the continuous case, then we'll just say the probability that yi is less than q of tau is equal to tau. Okay. So what does quantile estimation do? We just talked about the case of least absolute deviations, which identifies the median. So in quantile regression, in the leading case where we specify a linear function, we specify a linear function, and the intercept and the slope explicitly are shown there as being a function of whatever quantile we've chosen. And of course, this has become quite popular so that we can see how changes in the covariates change not just the mean of the distribution of y or the median, but how it affects various other quantiles in the distribution. The estimation method, there's a function that identifies a quantile, just as I was mentioning before how when we pick an object from a distribution, either a full distribution or a median or a mean or whatever, there's an objective function for which it is a solution to a population optimization problem. And in the case of a quantile, it's the so-called check function, which is written right here. I should have put a graph up, but this is just a function which is linear on each side of 0. Its slope is tau to the right, and its slope is, in absolute value, 1 minus tau to the left. And this is the thing that identifies the quantile, the tauth quantile, conditional quantile of the distribution of y given x. So if, in fact, the quantile is linear, then solving this minimization problem will consistently estimate it by the usual arguments, because this is actually a continuous function. It has the kink at 0, but it is a continuous function. So the general kinds of consistency results apply directly. It's the difficulty is in doing the large sample analysis, although it's pretty much been worked through. So you can look, say, at Mansky's book on analog estimation methods if you want to be convinced that, in fact, the median, the conditional median, does minimize the expected value of this objective function down here. Okay. So the reason why deriving estimation is a bit tricky too. It's not as if you can just use standard methods for smooth objective functions, but these things have been programmed up now, and they're doable for even large data sets. The asymptotic normality is the reason it's tricky is because if you try to differentiate this objective function twice, well, it's not defined at 0, but everywhere else the Hessian has got to be 0, and so the usual methods of expanding out in a Taylor series expansion just don't work anymore. Okay, but if you like those kinds of details, Roger Conker's recent book has references and lots of conditions under which this holds. Okay, something that's more interesting is you see lots of studies where a sequence of quantiles is estimated for different parts of the distribution, and of course, in almost all cases, those quantiles are all assumed to be linear. And one might ask, well, could all the quantiles really be linear functions of the same set of x's? Well, under strict assumptions, yes, but generally no. So one question this has been recognized for some time, but there's been some recent work actually characterizing what quantile regression is actually identifying when, in fact, the quantile is misspecified. So this is an easy exercise in the case of regression, because we know that if we have specified a linear function for in the case of least squares, then it's easy to show that, in fact, if the regression function, the population regression, is generally some function mu of x, then the parameters that we're estimating are the best linear approximation to mu of x in the mean squared sense. Okay, so this gives us a very simple way to interpret what we've done. We're just choosing the linear function that best approximates the true mean, where best is defined in terms of minimum mean squared error. Okay. By the way, there are some assumptions under which this, the betas that we get from least squares could actually be either the average partial effects of the true conditional mean, or at least proportional to them. This is work that goes back to the mid-1980s by Paul Root and Tom Stoker and others, trying to characterize when linear regression could actually estimate something interesting in terms of the actual conditional mean. But those assumptions are actually quite restrictive. It's more of an aside here. So as I mentioned, this formulation of linear quantiles as an approximation has certainly been recognized for some time. But other than that recognition, there hasn't really been much formal available. And until recently, Angrist, Chernozhukov, and Fernandez-Val have this nice paper where they characterize the probability limit of the quantile regression estimator when the true quantile is not actually linear. So just to simplify the notation a little bit, put the intercept back into x, so I can just write beta here. And then this is the conditional quantile function, the true conditional quantile function, q sub tau of x. Well, what they show is that the quantile function, the linear approximation obtained from minimizing this check function asymptotically has the following interpretation. It actually minimizes a weighted mean squared error away from the actual quantile function. So there are actually a couple of ways they characterize this problem. One is this weighting function that depends not just on x, but actually on beta as well. So when you minimize this over beta, you're actually choosing the weights as well as the discrepancy between the linear approximation and the quantile. But the weight function looks like this. And what it's really doing, so this is the density of y given x, and it's being evaluated at some point on the line between the linear approximation and the actual quantile. And then there's this weight out front, and so this is being averaged over all possible values of u, where you're giving more weight to points that are closer to the actual the true quantile function. So this does give a characterization of what's happening in this case. Whether that speaks to you or not, I don't know. But it is kind of interesting that the characterization is in terms of a mean squared error, basically, a weighted mean squared error. So it's not in terms of an absolute value even. It's actually a mean squared error that's weighted. And you can look at their paper for other ways that they use this result. They provide a way to interpret partialing out in a quantile regression and so on. But in any case, this is kind of interesting to show that there is an interpretation to what quantile regression is doing in the misspecified case. Now, in terms of computing standard errors, this can go through fairly quickly. Mostly the interesting thing is to know which standard errors are valid under which kinds of assumptions. If we assume that the quantile is actually correctly specified, then the two matrices that have to be estimated are this A and B matrix. This is always easy. Tau, of course, we've chosen because that's the quantile, and so then it's just the x prime x matrix divided by n. And this turns out to be the hard matrix to estimate, the one, interestingly, in the outer product of the sandwich in this case. And Powell basically showed one way to do that is to use, well, this would, if we took this part outside instead of having it summed in with xi prime xi, this would be just a histogram estimator. But unless you're willing to assume that the error is independent of the x, you generally have to have it inside the function here. So, of course, we have to actually choose this parameter h sub n, which is shrinking to 0, but not too quickly. You know, people have suggestions for how one should choose these so-called bandwidths. So the main point in putting this up is this is not entirely automatic, but probably you're just going to use the ones that are reported by whatever software you're using, or who knows, you might even want to program it up yourself, I suppose. There is an interesting point here in that how this works is very similar to why the standard Eicher-White heteroscedasticity robust standard errors work. It's not that this is supposed to be estimating the expected value of, if you go back here, it's supposed to be estimating this, and it's not as if each one of those terms gives us a good estimate of that part, but together it gives us a good estimate of the expected value here. Okay, so as I said, if we assume independence between the error term and the x, which again is a fairly strong assumption, especially if you're doing it across different quantiles, right? You can't really have independent of the errors across every quantile except in very restrictive situations. So that's what the formula turns out to be. And mainly, I'm pointing this out because this is, for example, in Stata, this would be the default, okay, which is to actually act as if the additive errors are independent of the x's. Okay, and that's what happens in this case is the density is estimated using this histogram. And of course, you can smooth this out if you want by using a kernel estimator of the density at 0. But since these are just going into standard errors, it's not clear that one wants to go through that. Okay, so if the quantile function is misspecified, then this estimator doesn't work, even if we estimate A in this way. The resulting variance matrix is not robust to misspecification of the quantile function. In that case, there's a different estimate of B, actually, that needs to be used, and this has been worked out, and it's also a simple adjustment to the usual estimator. So the most robust estimator uses B hat in this formula and A hat in the formula that I just had up there in 18. And hopefully these will become options that are computed routinely when you do quantile regression. That I haven't checked this for sure in Stata 10, but with Stata 9, you only had the option of using the completely non-robust version of the variance matrix. Now Han did work out that the Bootstrap works in this case, although it doesn't, as implemented on the non-smooth objective function, it doesn't provide the asymptotic refinements for t-tests and confidence intervals. Joel Horowitz has a nice chapter in the handbook of Econometrics that discusses how one one can do that adjustment. Okay. Let's see, just to have some numbers to look at, this is just an example generated from a data set that Alberto Abadi used in a case where he was actually allowing some endogeneity of a binary treatment. That's not done in this case, but you can see that this, when you apply quantile regression to something like a wealth variable, this is net total financial assets, you get fairly different estimates depending on what point in the distribution we're looking at. You can see the relationship between financial wealth and income for the average is quite strong, and it's quite a bit less strong at the median. At the upper quantiles of the distribution, it's strong, and then it's very, very weak at the lower quantiles. Some interest is given to this variable, which is eligibility in a 401k plan, with the idea being that while this has a large effect on average financial wealth, this is in thousands of dollars, it's very different depending on which part of the distribution you look at. In fact, if you keep going up the distribution, the effect keeps getting stronger and stronger. So clearly eligibility in this particular kind of pension plan has a much larger impact in dollar terms, certainly at the upper ends of the distribution. Okay. Unfortunately, these standard errors, these are the ones reported that act as if these quantiles actually are all linear in these x's. Okay, so what about quantile regression with endogenous variables? Well, certainly some stuff is known, but it's not as clean as when we use zero correlation assumptions between errors and instruments. So suppose we start with a model and we just write this model down. Y1 is a linear function as usual. And in fact, it's not entirely clear when we start talking about quantile regression or even least absolute deviations what we generally mean when we say Y2 is endogenous. We're not necessarily going to define it in terms of a correlation between Y2 and U1, although that certainly is one possibility. But let's proceed with this and see where it goes. So the Amemia's two-stage least absolute deviation estimator was the first one, I think, to deal with endogeneity in least absolute deviations estimator. And it adds to this a standard linear reduced form. So if you just looked at this and this, you would just think this is the usual setup. And now the question is, how are we going to estimate the parameters? Well, this estimator is done, well, in two steps, just like you can do two-stage least squares. In this step, either OLS or least absolute deviations is used, and then fitted values are gotten by using the z pi 2 hats, and then y2 hat is plugged in up there, and then least absolute deviations is carried out on the equation with the fitted values. So the question is, when does this give consistent estimates of parameters in the so-called structural equation? Well, certainly some symmetry has to be floating around here, and the easiest way to think of it is that, well, again, bivariate symmetry between U1 and V2 is certainly bivariate symmetry in that distribution is certainly enough, and because what happens is implicitly, of course, when you plug in y2 hat, there's a linear combination of this reduced form error that gets put in there. So the weakest assumption you're making is that there's a linear combination of U1 and V2 that has a symmetric distribution. Okay. Now, so that's what, this is the linear combination that is being plugged in there. Of course, you could do this as via a control function approach under the same kinds of symmetry assumptions by writing U1 as this linear function of V2, and then E1 would have a symmetric distribution conditional on V1 and the exogenous variables. And so instead of putting in Y2 hats, you can put in V2 hats and do least absolute deviations on Y2 and V2 hat. Actually, I'm not sure that I've seen this done, but I should say that this is just something that occurred to me after thinking about control function methods. Presumably a t-test on a VI2 hat to test for endogeneity is a legitimate thing to do in this case, although the asymptotics, I'm not sure, have been formally worked out. So it's the interpretation of doing least absolute deviations in these cases is a little strange, because if you start off with a structural model and you want to argue that the reason Y2 is endogenous is because it's correlated with some omitted variable, well, you have to assume lots of symmetry to get back to this equation where this error term here is symmetrically distributed. So if you just started off saying what I'm interested in is the median of y1 given z1, y2, and say some omitted variable r1, and because what I'd like to do is be able to control for this r1 and see what the effect of y2 is on the median, this conditional median, well, of course, if you're going to interpret alpha 1 in that way in the end, then you're going to have some symmetry of the distribution of the omitted variable, and it's going to have to be some sort of joint symmetry with the omitted variable and then the extra noise. So in the end, it's not especially clean in the context of estimating models by usual instrumental variables with omitted variables. We don't have to assume things like the omitted variable has a symmetric distribution in order to make sense of what we've estimated in the end. Okay, now, in the case of a binary endogenous variable, there's some additional work available, and this looks at the general quantile regression case. So there are papers by Abadi, Angrist, and Imbens that look at this problem. And it's in the context of estimating treatment effects. And Abadi actually looks at various features of a distribution, and the AAI paper focuses on quantile treatment effects. So the treatment in this case is binary, and call it D, to be consistent with their notation. And this is set up in the potential outcomes framework that actually, of course, it's closely related to the local average treatment effect setup, where you have a binary instrument Z, which is most easily thought of as eligibility for some sort of program, and then D is actual participation, and then there are potential outcomes Y sub D in both states, with and without treatment, or without and with treatment. And then, of course, there's the counterfactual treatment states too, that treatment without eligibility and with eligibility. And the usual setup here is the observed data consist of the covariates X, the eligibility Z, and then D and the observed outcome Y. Okay. So they study treatment effects for compliers. That is, you've already seen this before. These assumptions are actually fairly close to what we saw before. This is the unconfoundedness assumption, for the instrument conditional on X, probability of being eligible conditional on X can't be 0 or 1, and so on. This is the monotonicity assumption that is used in a lot of this literature. Okay, so under these assumptions, they show that treatment is unconfounded for the conditional on X for the population of compliers. Okay, so in other words, this is the usual thing. The distribution of the counterfactual outcomes conditional on treatment in the X's and for the population of compliers is unconfounded. Okay. That means that the treatment effects can be based on this distribution, which is the observed Y given X, given observed treatment, and then the problem is that we can't observe this population, this subpopulation, which is for the compliers. But for the moment, let's assume that we can and specify a quantile function for the population of compliers and say that it's linear in the treatment and the covariates. Okay. Now, so this is one of those cases where to consistently estimate these parameters, what you would like to do is use a subpopulation, but in fact you can't identify what that subpopulation is. So you're stuck with this larger population, and the question is, how can you identify these when you'd like to be able to condition on a subgroup? So one way to think about this is to define a dummy variable for the which is 1 for compliers and 0 otherwise. And so you'd like to be able to observe this, and then, of course, you could just do quantile regression on the population of compliers, and you would be done. So you'd like to be able to solve this problem, where this objective function G is just the check function, and then C would actually select out the subpopulation of interest that you can estimate this quantile for. So in some ways, I talked about inverse probability weighting earlier. This is in some ways the reverse problem. Is there you're trying to take a selected subsample and make it representative of the population. Here you have a population, but you would like a subpopulation. So you can't do this because C is not observed, but interestingly, they show that they can actually estimate the conditional probability of being a complier conditional on everything else that shows up here, Y, X, and D. And so it's a simple iterated expectations argument to show that this expected value is this, because this is just the probability of being a complier conditional on all of these observed variables. And of course, you could always say, well, I can turn this problem into this problem, but if you can't estimate this probability, then it doesn't do any good. Okay, well, as it turns out, it can be estimated. I see there's a notational problem. That should have, to be consistent here, that should have a V subscript, and so should it there, because this is all the same function. Okay. So under the assumptions, what's interesting is that the probability takes this form, where pi and v are estimable because these are the probabilities of eligibility conditional on everything else you observe, and this is the probability of eligibility conditional on the covariates. So once these two quantities are estimated, then you can take this population problem and turn it into a sample problem in this way, where this, of course, just ensures that you don't use observations where this estimated probability is actually negative. Okay, so you could imagine even doing this in a fully parametric way, where these probabilities that underlie this are flexible logits or something, and you can refer to the Abadi et al. Paper to see how you do it in a series estimation way. Okay, now more recently, Chernozhukov and Hansen consider also quantile estimation, they start off with this general notion of a quantile treatment effect. And the representation they use that's critical is that, again, this is in this counterfactual setting, is that the counterfactual outcome on y is this quantile function, and the randomness comes through this uniform random variable u sub d, which, of course, can change across counterfactuals. And z is the instrument that's independent of the unobservables. Okay. So the key identifying condition, I'm going to have to run through this to get anywhere close to even talking about the panel data case, is, or I should say the key insight is that under the assumptions they impose, they can actually show that the quantile function Q satisfies this, what's essentially a moment condition. Actually, it's easiest to see down here. Okay, so one way to think about this is, well, they're trying to estimate this function Q. Now it depends on observables D and X. Of course, it's a function of tau because we've chosen the quantile. This is the indicator function. So this moment restriction right here, if we could condition, if D were exogenous, I guess that's the easiest way to think. If D were exogenous and so we could drop Z and put D in here, this equation would essentially define the conditional quantile. Okay, this with x z replaced by xd, where d is exogenous, this defines the conditional quantile. So one way to think about their work is that they basically provide justification for taking the moment conditions that would occur under exogenous treatment and justify using essentially the analogous moment conditions under endogenous treatment where they have an instrument for treatment. This is actually least absolute deviation, two-stage least absolute deviations. Certain versions of it can be motivated in the same way. So there's something that they call a quantile regression instrumental variables estimator, which in special cases actually turns out to be the same thing as two-stage least squares if you were to replace these moments with the usual conditional, the zero conditional mean assumption. Okay, I guess I'm not going to say too much about the panel data case here, but let me just highlight a couple of things. If we just want to do quantile regression on panel data and not explicitly introduce unobserved heterogeneity, then of course using the data pooled across I and T is conceptually quite straightforward. Okay, we might have, and we might put in time effects or whatever to allow the quantiles to shift over time. The one point to make, I suppose, is that just as when we do least squares with panel data, and there might be extra serial correlation, we really should adjust the asymptotic variance for possible serial correlation in the quantiles as well. There is an assumption under which we don't have to do that, but that means that the quantile function has the dynamics completely specified. So in general, though, you have to use this kind of typical formula where you have to account for all of the pairwise correlations in the score, where this is the score function, which is, acts like the first derivative of the quantile function, and this is the kind of formula that shows up quite generally in nonlinear models. I think David Drucker at Stata interested in programming these up, because now if you try to do quantile regression with a cluster option or something in Stata, it doesn't happen. Okay. Let me just spend maybe just 3 minutes talking about the problems with unobserved heterogeneity. I think it clearly makes sense, even if we only think linear quantile functions are an approximation to reality. I think it makes sense to specify models like this, okay, where the quantile is linear in the covariates, and then an additive unobserved heterogeneity. So since the thetas would have a direct interpretation as being partial effects on the quantiles, it would be ideal if we could come up with estimation methods that don't restrict this distribution in any way. That would be analogous to the so-called fixed effects estimator for estimating conditional means.